Hello everyone, in this video we're going to discuss about Genesis. It's the new simulator, differentiable simulator actually, and that's very fast compared to Isaac Sim, Isaac Lab, Ujoko, and simulators like this. And this is the documentation that you can check. I'll let the link in the video description. You can check it out. I really recommend you to read all the documentation about it. I'm not going into too much detail because there are a lot of videos already about Genesis that you can check out. I will let the video link of those videos in the description. But I think it's important to discuss about the key features, like it's 100% Python based, very easy to use. The developers did a really good job on this. Um, the installation is very easy, and there is a Docker image for the whole installation that makes it really even easier to install and use. Also, as I already discussed, uh, it has unprecedented speed, like it states here, if compared with other simulators like Isaac Sim, as I said. It's also photorealistic. It's differentiable. It's physically accurate. Uh, in other words, it's very fast without compromising the accuracy, the physics accuracy. Uh, and also, uh, there is the GitHub repository that you can check out. As I discussed, there is a Docker image file that makes your life very, very easy. All the installation steps are here. You can check it out. And for this video, I'm going to demonstrate the simulator by showing you three demonstrations. This is the code I have written to control the Franca robot. And before I do this, I'm going to show you the Docker that I'm using. This is the Docker that I found in this repository with this tag. This is the version I'm using right now. And I just created two additional scripts like this, build Genesis, and this other one to run Genesis container that I already executed here in the terminal. You can see it here. And after this, I attach it to the container. And here you can see that I'm already inside the Genesis container. So the documentation is really good. You can go through the documentation and see, for example, how to control your robot, how to visualize, how to perform parallel simulation, inverse kinematics, and all that stuff. In this example, I kind of organized all the code in different files just to make our lives easier and make the code easier to understand. And first of all, when you want to execute the simulation, you need to initialize Genesis. And to do this, you make gs.init, just this, really, really simple. And here you choose parameters like the backend device. If you're using CPU, GPU, RTX, or even Apple GPUs, I'm going to open this here. You have some instructions in this link. I'll also let the link here in the video description, but you can go here in the Hello Genesis tab and just check it out. As I said, you can choose between different backends like CUDA, Vulkan, or Metal. For Apple Silicon devices, I have a RTX in RTX 36 here, so I'll let it as GS GPU. Also, I'm not going to explain all the parameters here, and you can check in this link and just try to understand it better. But the first thing you need to do is initialize Genesis. After this, you must set up the scene. You need to create the scene for your simulation. And here you have a lot of parameters to configure your simulation. Seems to be complex, but this is not complex. You can go to the API documentation and check all the options you have here. The options will depend if you want to simulate a rigid body, uh, fluid dynamics, or I don't know, clothes. Depending on the goal itself, you need to choose between different configurations, but um, also you can configure the simulation step, the sub steps of the simulation. If you want more precision, you can increase the number of sub steps just to make the simulation maybe more stable. I'll let it as default. I think the default is 1. Yeah, the default is 1. Of course, you can also hold control and go inside the class just to see the doc string and try to understand it a little bit more. It's really good. And yeah, for this simulation, the time step is 0.01. In other words, if we, for example, create a loop with 200 steps, it will be 2 seconds. The gravity is the default one. We have some parameters like the resolution, the camera position, the direction that the camera should look. Actually, this is not the direction, it's the target position that the camera should look at. The camera field of view, the maximum FPS if you want to have a more stable simulation without too much discrepancy between FPS, and some visualization options, like if you want to show the world frame, the size of the world frame, if you want to show the link frames. But most of this you can configure when your simulation is opened. I will show you how to do this. Also, you can choose between renders like ray tracing or rasterizer. Ray tracing here is really slow on my GPU. It's a 3060 GPU. Of course, it will depend on the number of meshes you have, textures, etc. So if you want to see the simulation window itself, you set it to true. If you want to show the FPS in the terminals, here it's variables. There are a lot of, how can I say, logger messages showing the FPS in each scene step, which may be a little bit annoying depending on your goal itself. So, but yeah, after you create the scene, then you can create the entities. So here you can create, for example, the plane, the ground plane itself, and set its materials. Here you had a lot of options as well. You can set the visualization mode. Here you can see all the options you have. For example, for the visual thing, like if you want to see the visual collision or STF, if it's a deformable body, you can set it to visual particle or reconstruction. But it's the window. Yeah, here. So you can change, for example, in this cloth that I'm going to show you, cloth simulation. You can see the particles or only the clothes itself. So also, I'm going to add, as I said, a plain clothes for the demo number 3. And also I'm going to add a Franca robot in the scene. I'm creating a dictionary to store the cloth and also the Franca robot. And for this robot, I created a I separated in another file called franca.py with all the configurations we have to do for each robot. And just to make it more generalizable for other robots like UR5, uh, I created a class that we can pass the Mujoko definition file, the robot initial position, orientation, uh, the name of the end effector link, actually, the robot scale, the gains, position, velocity, uh, the force, the upper bound, lower bound, the material, the index of each joint, for example, the gripper and the robot joints. And in this class, I wrote this class just to, as I said, make my life easier when I use a different robot. And in this class, for example, I initialize the PD, proportional derivative control, with all the gains I want. And I made this method just to initialize and set up the control gains. Also, to plan a path to the desired position and orientation. Also, another method to plan and execute the path to the position, to the desired position. We do this because here in Genesis, I noticed that we need to plan a path and then write a for loop to wait the robot to reach this path. And also, we need to write another for loop just to wait the robot to reach the goal position. So I wrote this class just to plan the path, execute the path, and wait for path completion. And in this method, we have I created another method that's called is position within tolerance. I'm comparing the position of the gripper and the effector and the goal position and waiting the robot to reach this position. I'm still not comparing the orientation of the end effector yet. I'm planning to do this in the future, but once the robot reaches the goal position, it will uh, break the loop and return to this method, and it will finish the path execution. So yeah, there are a lot of others methods that can help me. For example, get in the vector pose. Let me see what else. Yes, this execute path. If we have other waypoints we want, we can pass each waypoint inside a loop and just make the robot reach the desired DOF position, or the position of each joint. Here in this method, demo hard reset, we can add a sequence of poses with the desired joint commands and the number of steps to keep the robot in this position. There is another method called date PD control. Here we just control each joint of the robot depending on the type of control we have chosen in the robot setup, like position control, velocity, or force control. And this setup entity creates the robot in simulation using the Mujoko file. I'm just going to change this in the future so we can choose between different formats like URDF. Here there's another method called set control gains. As I said at the beginning of this video, that we should set up the control gains for each joint. the positional gains and the velocity gains. So yeah, after everything is set up, we uh, we create this entity like setup Franka robot. It will create an instance of the class and return it to the entity dictionary. So we have all the entities in the simulation from this dictionary. That is these entities here. After this, we should build the scene. And here you can create a parallel simulation, like setting up the number of environments, the spacing between the environments, the number of environments per row. And also you can see the documentation for this. I highly recommend you to check the documentation. Um, and yeah, after this, I create a new variable called Franken, and it's of this type here, the class that I wrote, and I get it from the entities dictionary, and then I initialize the robot by setting the control gains, and I'm going to also set up the initial position maybe afterwards. So and yeah, as I said in this first demo, I'm going to create a sequence of poses. This is the joint position I want, and this is the number of steps that the robot will be kept in this position. And after this, we're going to send this another command here and so on. So we're going to call the demo hard reset with all the desired pose, like this pose sequence, and it will execute the simulation with those pose that execute the simulation. And all of this is very clean. I prefer to do this instead of writing a big file with a lot of stuff that makes uh, the project really complex to understand. And yeah, and this is the hard reset. There is no physics acting on the robot. You can, in other words, you can bypass the physics here. If you press the I button, you can, for example, record a video, save image, reset camera, add camera rotation. I just pressed the A button. You can disable shadow. Shadow. You can see the face normals, the world frame. You can see each link frame. You can, oops, something happened. I don't know. Just a bug here maybe. But yeah, this is just about controlling the robot without physics, just like a hard reset. And for the second demo, I'm going to show you how to control the robot using the PD control. This is not hard reset. Here we are using the physics simulation. And for this, I've chosen the joints that I want to control by position control. I'm not going to use the velocity or force control. And here I initialize the PD control with all the desired joint indices. And then I execute the simulation for this number of steps. Then I update the PD control with the desired joint angles. So I step the scene after each iteration, and then when each reaches the total number of steps in this for loop, I reset the simulation so we can see the simulation starting again, and it will execute forever unless I close the window or press Ctrl C. Let me execute this. Here you can see all the information about the Genesis version. I think it's really interesting. Yeah, just straight joint commands yet. It's not. It's not fine-tuned. This is just for demonstration purposes. So, and yeah, here you can see the FPS of the simulation for just one environment. Of course, you can create a lot of environments here. And I'm still going to test this speed with different simulators in the future for different robot tasks. For now, I'm just using one environment because um, I'm going to show you the cloth simulation. And for non-rigid body simulation, we can't use parallel simulation yet. And that's what I found in the documentation. So um, now I'm going to show you the last demo. Uh, in this demo, I'm going to spawn a cloth with that has this material here. And for this, what's really important is to, if you want to simulate a rigid body and a PBD material, you need to configure this position-based dynamic option here. After this, you need to create a material for the plane, for the robot itself as well. Let me show you. Setup entity here. You need to associate the material that we created. What is it? Yeah, here. This material here. So after this, after you set up all the materials, this option here to configure the particle size, you can, for example, spawn the cloth in the environment. And in this demonstration, I'm going to actually, I took this part of this code from this. Let me try to find. There's a GitHub issue here around this topic. Globe simulation. Let me see. Yeah, this one. So this guy is trying to grasp a cloth in the simulation. So seems to be a problem that is not solved yet. Maybe the grasping stability should be increased here or fixed for this kind of simulation. But I'm following this topic here and I'm trying to simulate this as well. So if you find a way to do this, please let me know in the comments below or contact me in LinkedIn so we can discuss about it. But in this last demonstration, I set up the particle position of the cloth, one of the corners in this position, so the robot can reach the cloth and try to grasp from the corner. And then also I fixed the other corner of the cloth in the ground, so just to make the simulation more stable and fix the cloth on the ground. After this, I get the particle position of the cloth, and that's this one actually. I'm going to show you in this. Let me execute this just to explain it better. Um, and yeah, first of all, I'm going. I move the robot above the particle location and open the gripper. After this, I go to the grasp location. That's a little bit higher than the particle position. That's why I add this position here. Then I plan and execute the path to the position using the method that I discussed at the beginning. Then I close the gripper using this gripper pose, and then I move the cloth up above. So you're going to notice that the simulation is not stable, as I discussed. It seems to be an issue to be solved. I don't know. Let me know if I'm doing something wrong here. But this is what happens in simulation. So first of all, as I said, the corner of the cloth is fixed in the first position. Then I move the interfactor, close the gripper, and move it up again. So yeah, it doesn't seem to be realistic yet. Maybe just a configuration that needs to be not done here. I don't know. I'm going to check this and follow the discussion as well. And I will let you know if I get some news around this topic. That actually, I think that a lot of people are looking into this because now we have some powerful foundation models that can perform tasks in real life really well, uh, with, for example, folding towels and things like this. So I think that this simulation maybe is very benefit for the robotics community. If we can simulate this really well, I think that it will help a lot developers and researchers. So yeah. So that's it for this video, and I hope you liked. And I'm still studying and analyzing the simulator itself. I'm really enjoying studying this, and yeah, I will try to record more videos in the future. So thank you for watching, and see you soon.